Okay, we left off looking at limits at infinity, right? So as x approaches infinity, what's happening? And with a and b, those are going to be polynomials. Okay, they are, they will be. X to the fourth, we learned back in Algebra 2. It's going to be going either, well, up and up or down to down. Since it's positive x to the fourth, both sides will be going up, so it has to go to positive infinity. X to the third, we learned that's either a down-up or a up-down. Since it's a positive x to the third, it starts down and ends up. Okay, so that works with the polynomials. Now, C and D is more about rational expressions. Okay, because it's not just, a polynomial. On C, we started to talk about it a little bit, but do we have thoughts on there?
Only thing I can think of is 3x times x minus 4 and x times x plus 1.
Isn't it just 3 over 1? Because with the powers, you just use the coefficients.
Okay. When you're looking at the fractions, and this really, and it talks about a little bit later in this lesson where we officially review it, but I think of this one as our horizontal asymptote rules. If the bigger power is on bottom, it's a horizontal asymptote of 0, y equals 0. If the bigger power is on top, it's no horizontal asymptote, it's usually a Slian asymptote. If the powers match, if the biggest powers match, which in this case are the 3x squared and the 1x squared, then we go, there's a horizontal asymptote that is the coefficients. Okay, and so with that in mind, your horizontal asymptote is going to be 3 over 1 or 3. And a horizontal asymptote, where's your graph going to follow off to the sides? It's going to follow that horizontal asymptote. Okay, does that make sense?
Yeah.
Okay, so with that particular one, that's what I would say there. There's a horizontal asymptote at y equals 3. When you compare those, and that's because the powers were the same, right? And then, so as x approaches infinity, this would approach 3. And the same would be true if x approached negative infinity. Okay? As I said, we'll review asymptote rules a little bit more. Now, what would you say about D?
Would you just say slanted?
What?
When the bigger power is on bottom, slanted?
No.
Wow.
It's either going to be 0 or non-existent.
Okay.
I want to say this one is non-existent.
No, because that'd be the same as
0.
slanted asymptote. So when the bigger power is on bottom, it's 0. Okay, so here, the powers match. Here, 5x and x squared, bigger power is on bottom. When the bigger power is on bottom, there's a horizontal asymptote at y equals 0. Okay? They give a little bit more information than that, but I'm trying to keep it simple in terms of that's what, relating it to your previous knowledge. And this could also, I mean, if you think about reducing it, it's 5 over x, same idea, bigger power on bottom. Okay? Okay, moving along then. Okay, there are only 4 possible outcomes when you explore behavior to the extreme right or the extreme left. Okay? Example A, the curve can increase without bound. So as x approaches positive infinity in this specific example, what is my limit of approach? Positive infinity, right? So as we go to the right, my graph is going up, and so y approaches positive infinity. So this is a positive infinity example. So one possible outcome is positive infinity. And that would be the curve increasing without bound. B, the curve can decrease without bound. As x approaches negative infinity, so as we go to the left, what's this graph doing?
Negative infinity.
It's going down to negative infinity. So another possible answer is negative infinity. Okay. And those were the first two answers we saw yesterday. The next one, the curve can become asymptotic to the x-axis. If that's the case, as x approaches positive infinity, what are we approaching?
0.
The y value of 0, right? As x goes off to the right here and approaches positive infinity, we're approaching a y value of 0. That was example C that we just did. And then, if the curve doesn't become asymptotic to the x-axis, it could have an asymptote on a different specific y value. What about this one? As x approaches negative infinity?
3.
Can you guys see what's going on there? That there is, they don't have it drawn in, and they're not going to have an asymptote drawn in. You're going to have to be able to tell by looking at the graph, like, oh, that's what they would refer to as asymptotic behavior. Okay? And that is equal to 3. So that would be over here. As x approaches negative infinity, y approaches 3. Okay, so that's the graph version of it.
We didn't even have to do the bottom portion. We just didn't talk about it.
Well, I say we probably have. I was just getting ready to look and make sure. Are you okay with that, Eli?
Yeah.
Okay. Sorry, I was trying to figure out if you're just waiting or if there's a puzzled look on your face.
No, I'm trying to see if I need to sneeze or not.
Oh, okay. Maybe that's the look I was seeing.
Yeah.
Well, there's a little bit of a glare in your glasses, so I couldn't exactly see your eyeballs to know. So that was probably.
Professional poker player.
Okay, so let me just see. Have we talked about all this? I think we have. Revisiting the rules for finding potential horizontal asymptotes for rational functions from pre-calc and really algebra 2. You can use the idea of a limit in calculus to see why those rules hold true. If degree of numerator is less than degree of denominator, so bottom heavy, then the limit is 0. That is, so bigger power on bottom, then it's going to be the horizontal asymptote of 0. If the degree of numerator equals degree of denominator, so the powers are equal, then the limit is the ratio of the coefficients of the highest degree. Okay, that's what we did earlier. And then if the degree is greater on top, so top heavy, then it says the limit does not exist. It's just positive or negative infinity, possibly. We just don't really know. Okay? We don't really know until we look. That one's going to be a little bit different. Okay. Moving along then.
And all of a sudden, you have front and back.
Where we actually have to do a little bit more math.
Well, yeah.
We have 15 minutes.
Okay. And what I learned last year is every time I say, oh, yeah, we've got plenty of time, I then ended up crunching time at the bell. So, I don't know. And I'm not saying I will today. I'm just saying that seems to be what would happen to me. So, okay. Example 6. It talks about divide every term in the rational expression by the highest power of x that appears in the denominator. Then apply the properties of limits to evaluate each piece. Define the limit at infinity in behavior. But yet, they give us a graph. Okay, so what I'm going to try to do here is show this algebraically and why it works. As I said, they do give you a graph here, but we are going to, notice what it said. We're going to divide every term in both the numerator and the denominator by the highest degree in the denominator. So what's that mean we're dividing each term by here?
X squared.
X squared. So we're going to divide each term by highest power in denominator, which in this case is x squared. Okay, so I'm going to write this out. Might be kind of annoying to see, but it's the idea that I just want you to see what's happening. The limit as x approaches infinity. So 2x squared divided by x squared minus 10x divided by x squared all over x squared divided by x squared minus 8x divided by x squared plus 15 divided by x squared. Okay?
Why can't you just factor this?
Then you realize, yeah.
Because we're looking at a different technique. They're not all going to factor. Like, for instance, when we go to part B, it's not going to factor. Fair enough. I get it. It does factor, but I'm trying to show you the concept here, so stay with me. Limit as x approaches infinity. I'm going to clean this up a little bit. Now, 2x squared over x squared cleans up to be 2 minus, what's 10x over x squared cleaned up to be? 10 over x, if you will. In other words, if you cancel an x, the 10's still there. There's still an x in the denominator, so 10 over x for the moment. Divided by x squared divided by x squared is 1 minus 8 over x plus 15 over x squared. Now, the idea here is what happens to each of this when you plug infinity in, the idea of infinity. Okay, so think about this with me. 2 is just the whole number 2, yes?
Yeah.
So that's just going to stay 2 minus. When you take 10 and you divide it by a number getting bigger and bigger and bigger, what is that fraction approaching?
0.
0, right? Because 10 divided by 100, 10 divided by 1,000, 10 divided by 1,000,000. You're getting a smaller and smaller decimal, aren't you? That is approaching 0. So on top, you have the equivalency of 0. On bottom, 1 is 1 minus. What about 8 divided by a number that's approaching infinity? 0. Plus 15 divided by a number approaching infinity squared? Still 0, yes?
Quicker to 0.
Okay, fair enough. We end up with what here?
2 over 1.
2 over 1, which is 2. Okay. Could we have just factored that?
Yes.
Yes. Okay. However, we're trying to look at the idea of how this works. Okay.
Now you can see that being really easy, I guess.
Okay. Now, in all honesty, they give you the graph here, don't they? We can physically see that this is approaching 2. Okay, so they gave us a graph. But in all also, what's our shortcut? The powers match, so it ends up being the coefficients of the highest powers. This is the y. Okay, because these other pieces are going to tend towards 0. Okay? Question there?
Nope. Guess I just say, try to list the next one by yourself or something.
Well, and then probably better if you try not to look at the graph, but,
Oh, I didn't.
And again, that's the thing. We have a graph, we have a shortcut, but why does it work? That's kind of where I'm going with this right now. What is it you're dividing everything by? X squared. Okay. You want me to do it up here while you guys do it on your own? What happened? What'd you get on top?
0.
Yeah. 0 plus 0. What about on bottom?
1.
1 plus 0 plus 0. So you end up with 0 over 1, which is 0. Does that make sense with the graph? Yeah. You can see there, this is a different type of, it's a horizontal asymptote. Remember, horizontal asymptotes, there could be where the graph crosses it in the middle. That's okay. But as it goes infinitely off to the right and infinitely off to the left, it's going to stay around that asymptote. Now, did our asymptote work here? Yeah. Bigger power on bottom, y equals 0 asymptote. Okay? Again, just looking at the y's of why it all works the way it does.
The next one shouldn't exist, is what you're saying.
Which, at calc level, and we started, so at Algebra 2, we just said it didn't exist. At pre-calc, I started to say it didn't, there was no horizontal asymptote.
Plus or minus infinity on the last page.
Yeah. Well, it's not that it doesn't exist, it's just there's no horizontal asymptote. But in this case, what do we see happening? There's what I would refer to as a slant asymptote. We don't deal with those a whole lot in pre-calc. Okay? We deal with them a little bit more here. Now, you're seeing the bigger power on top, yes? If we do what we just did, dividing by the biggest power in the denominator, what am I dividing by? X. Oops. Got to divide him. Okay.
Well, I got infinity minus 4, so.
Okay. So if you're plugging infinity in, we've got infinity minus 4. 3 over infinity is going to be a 0. 1 minus 2 over infinity is going to be a 0. Okay, so infinity minus 4. What is infinity take away 4? It's still a concept of infinity. Okay, it's still approaching infinity. You can't really take 4 away from infinity. Because what they'll say is infinity's not a number. It's a concept, right? It's the idea of approaching infinity. So, now, a couple of things. So, I guess what we kind of need to transition to here is bigger power on top. No horizontal asymptote exists. Very possibly a slant asymptote exists. Now, does this make sense that as x approaches positive infinity, where's my graph going to go? It's going to keep going up, following that slant asymptote and going towards positive infinity. Now, side note, how could we find that slant asymptote? In order to know the equation of that line, you want to divide numerator by denominator. Now, dividing numerator by denominator could mean polynomial long division, or because it's just dividing by a linear factor, what's the alternative to long division? I couldn't come up with a word for it for a moment. That's why I had a weird look on my face. Not short division, but synthetic division? Okay. Because what goes in the box?
2.
If we're dividing by x minus 2, it's the opposite of the sign. And then what goes next to this?
It would be 1, negative 4, negative 3.
Okay, coefficients.
And what is it? You multiply.
After you drop the 1,
Drop
drop that first 1, and then, yes, multiply and add. 2 times 1 is 2. Negative 4 plus 2 is negative 2. 2 times negative 2 is negative 4. Negative 3. You do get a remainder. But here's what I've usually seen, is that, yes, you get a remainder. I'll be honest, I just kind of ignore the remainder. What does the 1 and the 2 represent? The 1 and the minus 2 represent?
X minus 2, right?
X minus 2. Well, look at this. This line is approximately y equals x minus 2.
Well, that's just the denominator.
Okay. Well, it's coincidence. It's a denominator. That's pure coincidence.
So the answer would still be infinity, though, right?
Yes, yeah. But I'm just saying that that's a way you can find your slant asymptote. Not that that's something you have to do very much, but, you know.
Comes up on the AP.
Okay.
20 minutes. What page? Don't screw it up.
You got this.
Did you say don't screw it up?
Yeah.
Gee, thanks. Okay. On example 7, they ask us to summarize and discuss characteristics and end behavior at horizontal asymptotes and slant asymptotes based on your observation in example 6. I kind of feel like we've been doing this all day. But, so, the limit, so functions with horizontal asymptotes. Is example 6 what we just did? Yes. Who had horizontal asymptotes? That would A and B, yes? So A and B had horizontal asymptotes. And what did we notice about those answers?
Your integers.
Okay. And integers that matched with the, what were they the same as?
The asymptotes.
Yeah, the horizontal asymptote, yes? So, the way I have this, and I don't know how she has it written in hers necessarily, but the way I have this is that both of these limits, and I generalized and used B. Now, where, first of all, B, I don't know if you've seen this or not, is a member of the reals. Okay, so what that's saying, I said that both limits equal B, and I'm going to give a little more information about B. B is a member of the reals. That little, I don't know, it's almost like a kind of a sloppy looking E type thing. That's a little symbol. I don't know what it's called, but is a member of. That funky R, we used that somewhere, didn't we? Or do I use that in calc? Okay.
I feel like we used it somewhere. It looks familiar. But
Okay, well, that fancy R represents real numbers. So that's saying B is a member of the reals. And what did we just talk about? Y equals B is I'm still going to use the abbreviation HA, a horizontal asymptote of the graph Y equals f of x. Okay, so f of x, what we are trying to find the limit of. Okay, so that's generalization. Anytime there's a horizontal asymptote, your limit's going to be, as it approaches positive negative infinity, is going to be equal to that horizontal asymptote. Now, functions with slant asymptotes. Well, that was example C. What was example C equal to?
infinity.
Infinity, or it could be equal to, depending on which way that slant asymptote goes to, it could also be equal to negative infinity.
Yeah.
So both of these, it all depends on which way the graph is going and which way the slant asymptote goes, but either positive or negative infinity.
Which is exactly what the page before last page said. So.
Okay. Now, my comment here is to use long division or synthetic division to find the equation for slant asymptotes. And then it says to test values to find end behavior. and in that case, it's going to end up equaling positive or negative infinity when you plug it in, but it gives you the idea there. Okay? So, comment I'm going to put here, use long slash synthetic division to find slant asymptotes. Now, if you need to, you can test values to find end behavior. I'm not even sure you really need to do that necessarily, but okay. We've talked about how we, in calculus, we're using new language. You have to be able to justify come AP test time. Okay, so here it talks about the limit definition justification of a horizontal asymptote. And this is basically saying that if the limit as x approaches positive infinity and negative infinity are, either of them are equal to a number, then that number is a horizontal asymptote. And that is our official justification that I'm going to write out. Okay, so I'm going to say if the limit as x approaches positive infinity of f of x equals b, or we're going to do this the other way also, the limit as x approaches negative infinity of f of x equals b, then y equals b is a horizontal asymptote of y equals f of x. So of the function, basically. So if either time x is approaching positive or negative infinity, it's equal to a number, we know there's a horizontal asymptote there. That's what that tells us. I feel like sometimes they've even skipped number 8 when I'm out of time because it says challenge. Are we ready for number 8? It says to use algebraic techniques to find the limits for g of x equals 3x minus 3 over the square root of x squared plus 4, whose graph is shown. Which means we kind of already know the answers. But how could we do this if we didn't already have the answers? Okay, so if we didn't already have the graphs, I guess we don't have the answers, but let's look. I'm going to look at positive infinity first. I'm going to look at the limit as x approaches positive infinity of 3x minus 3 divided by square root of x squared plus 4. Now, we go back to what we did on, was it the previous page? Yes. But it's not x squared.
X squared root it.
Okay, see.
Just be x.
But 4 is under the graph.
Okay, so, right ideas. Okay, it's the square root of x squared, which in generalized thinking is equivalent to x. Because it's under a square root, we're actually going to say the absolute value of x is what you're going to divide everything by. Now, if we want to shortcut this, you know it's only going to be the first two terms that matter, really, right?
So you're gonna leave the square root on there too, right?
I'm sorry, say that again.
I don't think so matter. Oh,
Okay. Now, before we go on, let me talk real quick. What is the idea? Because we have to divide 3x by the absolute value of x, yes?
So just state it's going to be positive.
Okay. In this problem, since x is approaching positive infinity, basically what can happen then? That's going to be positive, and so those can just cancel. Now that's because x is approaching positive infinity. So if we actually go through, I'm going to go through and divide it out, I think. So that means 3x divided by the absolute value of x is going to become 3 minus,
0.
well, I haven't plugged mine in yet, but I was going to say 3 over the absolute value of x, but yes, we'll be 0 here in a moment. Under the square root, because you're under the square root, you can think of it as just dividing by the x squared here, because we're under the square root. Okay, because this was the square root of x squared, so while you're under here, it's x squared divided by x squared, which is 1 plus 4 over x squared. What's happening there when we plug in infinity? You're going to have 3 minus 0 over square root of 1 plus 0, which all ends up to be 3. Does that agree with the graph over here? It does, doesn't it? Now, alternative. What if x is approaching negative infinity? Okay, you're still dividing by what? You're still going to end up dividing by absolute value of x where appropriate. Okay. Now, what's going to be different this time? When we do 3x divided by the absolute value of x, but in this scenario, we're approaching from negative infinity. So as we approach from negative infinity, what's this going to equal? Up here it equaled 3, yes?
Negative 3.
It's going to equal negative 3 because that x value could be negative. It will be negative. Thank you very much, sir. So now, when we go through and do this dividing, the limit as x approaches, I almost forgot my negative infinity. On top, it's going to become negative 3 minus 3 over absolute value of x, and then still going to be the square root of 1 plus 4 over x squared. All of that to say what changes? It's going to be a negative 3, yes? And notice, does that match down here?
Yep.
It does. Okay. And again, this is all about how do you work this type of problem when you don't have the graph? Okay. This isn't something that factoring's really going to help with or anything like that. How do you work it when you don't have the graph? Okay? So 1.7 homework for tomorrow.